This is Pre-Calculus, Functions and Graphs. I'm Mr. Stark. I'm glad you're here. We're still on topic 2, learning about functions and their properties. This lesson, lesson 2C, is all about boundedness, extrema, and symmetry. There'll be a short tutorial about finding the max or a min on a TI-84 calculator. So follow along using this document, and let's take this lesson to the extreme. Bounded functions have a ceiling, a floor, or both. Let's try to understand boundedness graphically with these three situations. First, an example of bounded above. Here's a simple parabola that's opening downward, and there's a point at which the curve doesn't go any higher. Therefore, this function is bounded above. Bounded below can be visualized by a function that has a floor, like this absolute value function. There's a point at which the function doesn't go any lower. Finally, a good example of a function that is bounded above and below is the sine function or the cosine function. If you're not familiar with the sine function, it's a trigonometric function that goes up and down forever between -1 and 1. Unless it's transformed, the sine function has a max of 1 and a minimum of -1. Speaking of max and mins, local and absolute extrema are just that, maximums and minimums. The local descriptor means that the max or min happen on a specific interval. So let's talk about that first. Jot this down. If f of c is greater than or equal to f of x on I, and I'll explain some of that later, then f of c is a local max. Right below it we have if f of c is less than or equal to f of x on I, then f of c is a local min. Okay, a few points of clarification. C is an x value that you choose based on the function, because f of c is a point of interest on the graph. While there might be a really low point on the graph, there might be some other low points as well that aren't as low as the lowest point, and that's what's called a local minimum. It's just where something interesting happens. The curve goes up and then comes down, or down and then comes up. And the other thing, the capital I is an open interval from A to B. So it's a specific interval or window that's part of the larger domain. And when we're looking for these local mins or max, it's not like we're choosing a specific interval. We're just looking at the graph and we're like, oh, there's a local min, I think, and there's a local max. Let me look a little closer. Now let's extend the definitions of local max and local min to absolute max and absolute min. For the first line I said, if f of c is greater than or equal to f of x on I, then f of c is a local max. If we say on the entire domain, then f of c is an absolute max. Notice how I extended the interval to include the entire domain. And if we include the entire domain and we say that a certain y value is a max, then it's the absolute max. It's the max that's the biggest max. Okay, maybe that was too extreme. Sorry. So for the second line, if f of c is less than or equal to f of x on I, if we say on the entire domain, then f of c is an absolute min. I did it again. I widened the interval to include the entire domain so that I could say, well, if I find a min on the entire domain and it's the smallest min, it's the lowest min on the entire graph, then we call that the absolute min. I want you to see that there are two situations here. One, we have just a specific interval and we find a max or a min, and when we do that, we call that the local max or the local min. But the other situation is when we consider the entire domain and we've found the max and the min, the largest y value and the smallest y value, then those are called absolute. Now it's time to get extreme on your TI-84 graphing calculator. If you have a TI-84 graphing calculator handy, I would like to show you how to find the min and the max of the sine function that we just talked about a few minutes ago. Pause the video right now if you need to get that. So here we go. I'm about to narrate this tutorial, and if it goes too fast, just pause the video so you could catch up. I have my calculator on and I go directly to y equals and enter the sine function. It has to be in radian mode, notice at the top. After I enter that, I press zoom 7 for zoom trig. You could just press graph as well. Then the min and max feature is second trace, which is the calculate feature, and I go down to minimum. The other options you have on the screen are max, obviously right below, but you could also just enter a value in or find the zeros of that function. Okay, now it asks you a question, left bound. So we arrow left to the left of a minimum. Notice where the minimum is. And then I arrow right to the right of the minimum. And then it says guess. It's asking you to guess where the minimum is. So I did. And I actually guessed like right on the minimum, but that doesn't always happen. And now I want to point out that I chose that minimum to the left of the y-axis, to the left of the origin, for no particular reason. It was just I was interested in that little region, and I would call that little region maybe from -2 to 0 on the x-axis as the interval that we're interested in. Okay. Now notice that it says on your screen minimum x equals -1.57, etc., and y equals -1. Y equals -1 is the minimum. The y value is what gives you the minimum, the function value. Okay, back to the tutorial. The next thing I do is I'm interested in finding the max. So I press second trace again and go to 4, and it asks me the same questions. It says left bound. Okay, so I find this peak over there to the right, press enter, move to the right again, press enter, guess. Okay, notice how I don't go to the very peak, it's at 0.96. And then it gives me the max. Notice how it says maximum now, and right below it says x equals 1.57. That's the location of the max on the x-axis. So that's helpful sometimes. If I were to ask the question, where is the max? The answer would be 1.57. But if I ask the question, what is the max? The answer is 1. And you could pretty much see that clearly on the graph. So then I continue, and watch what happens next. I press second mode to go to my main screen, and I press the X button, enter. That's kind of cool. What the calculator does is it stores that X value in for the X variable so that when you press X, enter, you have that value. So if we needed to use that for some other calculation, it's there, and all of the decimal places that go along with it. So now watch what happens. I kind of know what that number is, so I press second pi divided by 2, and that's pretty much that value. Now the last few decimal places are a little off, but it's an approximation. So what you'll learn later in the trigonometric functions unit is how the maxes and mins of sine and cosine happen at factors of pi. Oh man, that is totally extreme. The last thing to talk about is symmetry of a function. There are 3 types of symmetry. Symmetry about the x-axis, symmetry about the y-axis, and symmetry about the origin. Symmetry about the x-axis is not really a thing we talk about too much because when there is symmetry about an x-axis for a curve, it's not a function. It means that if x comma y is on the graph, then x comma -y is also on the graph, which means it fails the vertical line test. An example of this would be the sideways parabola defined by the equation x equals y squared. If you solve that equation for y, you get y equals the square root of x, which is the top part of the parabola, and y equals negative square root of x, which is the bottom part of the parabola. When a function is symmetric about the y-axis, we say that that function is even. We can confirm that a function is even by showing that f of -x is equal to f of x. In other words, if we plug in -x into the function, then the result is the same as the original equation. Let me show you what I mean. So for f of x equals x squared, if we plug in negative x, so f of negative x, we get quantity negative x squared. And if we perform that operation, negative x times negative x, we get x squared. That is the same as the original function we started with, therefore that function is even. When a function is symmetric about the origin, we say that that function is odd. We can confirm that a function is odd by showing that f of negative x is equal to negative f of x. Meaning, if we plug negative x into the function and we get the same function, just negative, every term is the opposite as the original sign, then it's odd. But let me show you what I mean. For the function f of x equals x cubed, we'll plug in negative x. So we have f of negative x, which is equal to quantity negative x cubed. And if we do that operation, negative x times negative x times negative x, we get negative x cubed. And because negative x cubed is the opposite or the negative version of the original function f of x, then f of x is odd. But why do we call them even and odd when we could just say symmetric about the y-axis or symmetric about the origin? Well, because if a function has all even powers and we plug negative x into every variable, then the negatives are going to multiply by another negative and become positive. And if a function has all odd powers and we plug in negative x, then the negative will be multiplied by itself, negative, 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 and it will result in a negative value. And looking at our examples, 2 is even and 3 is odd. That, my land-bounded learners, is the end of Lesson 2C. I hope you take your new math knowledge to the extreme and share it with the world. And I guess, don't forget to plant a symmetry before you get too old. See you next time.